Okay, thank you. So, my name's Dean. I'm a data engineer at Funding Circle. My world mostly revolves around getting data out of our operational systems and into our data warehouse. Spent the last couple of years using Kafka to shuffle data around. So I'm going to talk about how we use Kafka in our ETL jobs and some of the things I've learned while using it. There's a slight title change here. When I submitted this, I quite liked the rhyming in the name, and then 2 days later, I'm like, no, that's no good at all. So I just cut it out of that. So that's a picture of me when I started using Kafka a couple years ago. I really knew nothing about stream processing in general, but I was very excited to learn. So if you're in the same boat as me, or as I was, don't worry, I'm going to go over what Kafka is and stream processing in general. It's also a pretty good representation of how I feel today. I'm kind of new to this whole presenting thing, so I would never ask you guys not to heckle me, but if you could heckle me less than you normally would, it would be much appreciated. So I'm going to talk about how we use Kafka at Funding Circle. Then I'll talk about some of the major Kafka frameworks / libraries that let you use Kafka, but also how they tend to steer you towards a one-by-one message processing paradigm. That works very well in the operational world, but not so well for all analytical purposes. I'll explain why and how to avoid it. Finally, a little bit about dealing with errors in the stream processing world. So Kafka was originally developed at LinkedIn, then open sourced in 2011, and became an Apache project. The people who made Kafka also started a company called Confluent, which makes a platform that has Kafka at its core. Some of the tools I'll talk about later are part of the core Kafka, while others are part of Confluent. It's not super important which is which, just so you know that those terms may appear. So LinkedIn, when they were developing this, had a lot of services and a lot of different data pipelines. This led to a lot of reliability and scaling issues. So they decided rather than having to maintain and scale each and every custom pipeline individually, and that's the mess to the left here, they decided to build a single distributed pub/sub platform. So I've heard Kafka described many ways. Some say it's a distributed pub/sub platform. It's a distributed streaming platform. It's a central hub for real-time data streams. So what the heck does that actually all mean? So first, it's a pub/sub platform. You can have one or more producers publishing messages to a topic. Then you can also have any number of subscribers consuming from that topic. For the topic shown in this diagram here, producers have published 12 messages total to the topic. There's 2 consumers in this case. One has read 9 of the messages. The other has read 11 of the messages. In Kafka, it's up to the consumer to keep track of its current offset. So with Kafka, you end up getting what's called at least once delivery semantics. Once a message is written to a topic, it's guaranteed to be there, but it may be read multiple times by any given consumer. Since, there's no way to guarantee that a consumer will only read it just once. It may read the message, process it, and then fail before updating its offset. Because, you can't guarantee exactly once reads, in general, for performance reasons, the offsets are updated periodically instead of after each and every message. So now let's talk about what a stream of data or an event stream is. Say you want to know the balance of a bank account. Instead of just having an account balance like you would traditionally see in a relational database, you have a stream of credit and debit records. From those, you can easily derive what the final balance is. You can think of this stream as a log. New records just get appended to the end of this log. So basically, you have a whole bunch of topics, which are logs or event streams or whatever you want to call them. These topics live in a single system, which is Kafka. Early in its life, the people developing Kafka often referred to it as the global commit log thingy, which I think is actually a really good name for it, but didn't stick for whatever reason. Above, I've shown what 3 different topics might look like, each one containing some key value pairs. So is Kafka just a bunch of topics? It's kinda. But it's also distributed, which makes it fault tolerant, and it scales really well. So In order for things to be both distributed and scalable, there needs to be a way to split up a topic. This is done by creating multiple partitions for a single topic. So partitions are the concurrency primitive in Kafka. I'll go more into that a little bit later. Each message that gets written to a topic is a key value pair. So you can see there, the keys are 22 and 871, et cetera, and the values is a JSON blob. The key is what determines which partition the message actually gets written to. So in this example, the key is an account ID, and the message represents a debit or credit to that account. So ID 22 would always go to, say, partition 0, and IDs 871 and 19 would always go to, say, partition 1. Since the same key always goes to the same partition, events are always in order for any particular key. Now, these partitions can all live on different machines within a Kafka cluster. In this diagram, it's showing a topic with 4 partitions, P0 through P3. P0 and P3 live on server 1, P1 and P2 live on server 2. They could be spread across 4 servers or whatever. In this diagram, there's also 2 consumer groups. So any job or application would have its own consumer group. We could say group A is from, let's just say, some operational app, and group B is some ETL app, for example. I mentioned earlier that partitions are the concurrency primitive. What that means is in Kafka, you can have at most 1 consumer for each partition. The number of partitions determines the max concurrency. So in this case, consumer B is using the max concurrency. It has 4 consumers for 4 partitions. Group A just has 2 consumers, so each consumer is handling 2 partitions at the same time. This job, if they wanted to, could scale by adding 2 more consumers and process things a little bit faster that way. So how well does it actually scale? This is an excerpt from LinkedIn's engineering blog in late 2015. We now use it to process more than 1 trillion published messages per day, with peaks of 4.5 million messages published per second. That equals about 1.34 petabytes of information per week. Each message gets consumed by about 4 applications on average. So there's a lot of big numbers in that. 1 trillion messages per day is pretty good, as far as I'm concerned. Now at Funding Circle, we're not exactly doing 1 trillion messages per day. You can probably shave a few zeros off the end of that. But it's really nice knowing that we're not going to be hitting scaling issues. So a bit about Funding Circle. In a nutshell, we're a marketplace for loans for small and medium-sized enterprises. Business owners apply to us, and then we gather info for them, do the underwriting, and once approved, we list the loan on a marketplace. Investors can then purchase portions of various loans. So we may not have the scale of LinkedIn in terms of volume, but there is a lot of data required for this whole process to work. Less so in terms of rows, more so in the terms of attributes per loan application. Per application, there's going to be thousands of various attributes that we need to collect. So between this huge amount of attributes and also the fact that our business has been expanding into new countries, we needed a consistent and reliable data platform that could be deployed across all those geographies and work the same. So it's really important that all our applications have the exact same view of the world. Let's say that these applications are apps. They're definitely not. I wanted to use this naming convention, but no one would allow it. Those are Steven Seagal movies, by the way. Also, they make really good sprint names. But anyway, over time, the same bit of data tends to find its way into the database for multiple services. So here, Mark for Death talks to Hard to Kill, gets back some response, and then updates above the law with something. If a failure or a network partition happens or something during this, it's possible for some of the databases to be updated, but not all of the databases. You could hopefully have some really complex logic that would take care of rolling back across multiple databases, but in reality, that just doesn't happen most of the time. And so where that leaves you is with inconsistent data in different databases. So kind of gross. Over time, your services start to get more complicated and more of a spider web of communication from various services. So what we really want it to look like is something beautiful like that. So at the end, our goals are not too dissimilar from what LinkedIn was trying to do when it originally created Kafka. Before we go any further, I want to talk about loading data into a Postgres database. This will kind of tie into how we use Kafka on the data team specifically. So why Postgres? It's what we use for our data warehouse. With an operational system, everything is usually real time, so it makes a lot of sense to do individual inserts for every event. With a data warehouse, though, the total volume of data being ingested tends to be a lot higher. And often there are reasons to go back and reprocess a lot of back history and stuff like that. And so real time isn't as important, and it's a lot more load intensive. In the analytical world, you don't need exactly real time. You just need fast enough to get whatever report out. Whether that be every few seconds, minutes, hours, day, it doesn't really matter, as long as you're kind of meeting that cadence. So I just want to show some numbers. For a benchmark, I created a Postgres database in RDS, and then I created an EC2 instance to run the tests on. If anyone's really bored and has nothing to do tonight, the code I did is there. So basically, I ran 5 passes of all my tests and averaged the results between them. There was basically no deviation between any of the tests, so one run was kind of reflected the average in general. So these are kind of basically the queries I used to test the different types of inserts. The idea was for every ID I want to insert, first fetch that row from the database if it already exists. In this case, it didn't, but it's not so important. What I was really trying to do was simulate the round trips that happen in an ETL process. You usually have to get something from the database, get it back, do some transformation, and then either insert, update, or ignore the results that you have. I ran each test both in a single thread and tried it as well in 4 threads at a time. When running it in 4 threads, I took the total number of rows and just divided it by the number of threads. For the single inserts, this would be run in a loop for each and every row in that thread. So that top one's kind of in a for loop. For the bulk inserts and copy commands, it's just run once for all the rows in that particular thread. So I inserted 10,000 new rows into the table for each test shown. As you can see, the single inserts are far slower than the other methods. With relatively low data volumes, your ETL jobs can make that work, but it's not ideal. If you can keep up with what you're doing, but if you want to go back and reprocess data, it can be a bit of a pain. However, it took me a little bit of time to figure out how to actually do bulk inserts from Kafka, so I'll walk you through that a little bit later. So how do you actually use Kafka? You can just create plain old producers and consumers. However, those are a little bit low level, so instead you tend to use libraries or frameworks that take care of a lot of the heavy lifting for you. I'm going to talk about the first 2 options I tried, Samza and Streams. So Samza is a framework which, like Kafka, was developed at LinkedIn. The goal behind the framework was to get reliable jobs written as quickly as possible. So kind of, not super feature rich, but simple, easy to deploy, consistent. The framework takes care of a lot of the nuts and bolts for you, especially distribution fault tolerance. For every partition in the input topic, it will automatically spin up a consumer, so you automatically get the max concurrency available without having to worry about it. It'll take care of getting those consumers running across multiple machines if you have multiple machines available. If one of those consumers dies, it'll also take care of restarting it, redistributing the load, all that kind of stuff for you. So you don't really have to think too much about the distributed nature of Kafka if you're using Samza. It's pretty nice. So the way a SAMSA job is defined is using a properties file like this. You just kind of specify what your input topic is, what type of data are you going to be pulling off the topic, and what code should actually handle each message that you're going to process. So the actual code that you have to write is very simple. This example here is in Java. You basically just have a function that gets called every time there's a new message on the topic. From there, you can really do whatever you want. Write to a database, write to a new topic, whatever. Beyond that single function, you don't really have to worry about the details about what's going on too much. It's really nice, a lot of the time, but if you want to write to a database, it very much steers you towards one-by-one message processing, which, you end up hitting those speed issues we mentioned earlier. Then there's Kafka Streams, which came out much later than SAMSA, and it seems to scratch a lot of the issues from that framework. This list is a bunch of things that it addresses. One thing is it's a library instead of a framework, so it's super easy to include in an already existing app. It also does things like joining multiple streams, grouping data, aggregating, handle late arriving data, all that kind of stuff a lot easier. The goal behind it is summarized in this very scientific graph. They just wanted to give you a lot for, with a very simple DSL. Very scientific, yeah. If your input is one or more topics and your output is one or more topics, streams is the business. Like it's very nice. Unfortunately, if you want to do multiple processing, not so much. So streams has the concept of k-streams and k-tables. A k-stream is a record stream where each message is a self-contained bit of data. If you'd want to sum over the values in the messages, for example, in like a credit debit kind of thing, this is the type that you would want. And then there's k-tables, which is a changelog stream, where each message just has the latest state of a particular entity. So if you'd only want to see the most recent values for something, this is the kind you'd want. Yeah, so in this top one, each data point kind of stands on its own, and you need to see each data point to kind of get the final picture, whereas in the last one, you would only need to see the last record in order to see the current state of things. So k-tables are very much like a traditional database table in how you view them. Behind the scenes, there's still a stream of data, but it kind of abstracts those details from you. So streams has a lot of nice other features too. These ones above. I really tried to abuse these in order to get around the one-by-one writes, but I wasn't able to make it happen. So earlier I said that in our company's case, we're not processing a huge amount of rows by any means. Keeping up with the daily load is no problem, but I'm always finding reasons to have to slog through an entire topic from the very beginning. The usual reasons are because we're either pulling out a new field in existing data to add to our warehouse, or we want to fix some kind of bug that we found. I remember one job in particular where it had been running for months and months, and then we ended up finding a critical bug in one of our transformations. We wanted to reprocess everything from the very beginning to fix this bug. In order to do this with individual inserts into the database, I estimated it would take about 33 hours to run. So this is kind of the issue that led me down the path to start looking for a way to bulk insert from Kafka in earnest. As I said, I spent a day or two trying to corrupt Kafka Streams to get that to work, but couldn't get it to happen. There may be a way to do it. I just have no idea. What I really wanted was a way to handle a batch of messages at a time. Basically, I want n messages. If I don't get n messages in a minute, just give me what you have so far. After a long time of getting shut down, I was randomly clicking through the Kafka Java doc, and I accidentally clicked on the doc for just the plain old Kafka consumer, and I saw this method. Huh. Looks pretty good. Let's pull. So I know what you're thinking, you idiot. Why did you not look at the consumer to begin with? Well, when I had just started using Kafka, it was the first thing that I looked at. But it seemed a little too low level at the time. I was looking at it like, oh God, you have to manage all this distribution and stuff like that. I don't want anything to do with that. I'm just going to use Samza, and Samza is going to take care of all that for me. However, what I discovered later was I don't actually care about having a distributed consumer in most cases. I'm perfectly happy to have one single consumer in one thread on one machine doing bulk inserts. It's still way more performant than having 10 individual consumers each doing individual writes to the database. So in the end, the solution was just to create a plain old consumer and run poll in a forever loop. So with most things that I build, I'm happy to get it working correctly first and then worry about the performance later. Most of the time, this performance optimization step never actually happens, so I don't worry about it too much. But with this, it's actually really hard to switch from single inserts at a time to bulk inserts later. It could mean switching away from like Samza to an entire another framework, and it's probably also going to really affect your ETL code, since you're going from handling a single thing at a time to multiple things. So if you might have code that, for example, handles type 2 dimensions. It can be fairly complex. If you're going to switch from just handling a single entity to handling multiple entities, it can be a fairly big refactoring job to get that done. Thing is, once you're using bulk inserts, it's actually fairly trivial to either go from bulk inserts to multi-threaded bulk inserts if you really wanted to, or go from bulk inserts to using a copy command. For those of you who are not familiar with the copy command, it's basically, instead of using like a JDBC driver to write directly to the database, you basically dump your data to CSV and then use a tool to copy that CSV directly into the database. And it's really fast. It's just slightly more indirect. And so if you're getting fast enough speeds using the JDBC driver, I usually do that. So even a single-threaded bulk insert outperforms multi-threaded single inserts. So it's a fine place to start if that's what you're going to do. So in this benchmark, the single-threaded bulk insert took 7.5% of the time of the multi-threaded single inserts. With that 33-hour job that I mentioned before, once I switched it over, it actually only took 1.5% of the time to run. So it ended up being done in like 20 or 30 minutes instead of 33 hours. Not sure exactly why it performs better than the benchmark, but there's a lot more stuff going on behind the scenes, probably a lot more chatter to the database and that kind of thing. So as nice as the basic consumer is for getting data out of Kafka, Streams is still really nice for processing data. In the end, our ETL jobs have started to look somewhat like this. We kind of use Streams to do all the heavy lifting, the transformations, aggregations, all that kind of stuff, and then just dump it to an output topic. And then from there, just have a simple consumer job to pick up that data and take care of being the interface for the data warehouse. So that was the main thing I want to cover. The other thing I just wanted to talk about was dealing with bad events. There are two categories I want to discuss. Events that shouldn't have happened and events that didn't actually happen. So events that shouldn't have happened, this is when something happens by mistake and needs to be corrected. The classic example being an account being debited by mistake. Customer will notice, and then the bank will have to issue a credit to kind of nullify that debit. So, in a nice world where things are very clean and neat, there's an opposite event to any event to nullify it. Generally that's not the case. So if you do end up getting bad events on, you often have to create a brand new event that's kind of a cancellation of something. It can get pretty messy. And then there's another kind of bad event. So one thing we're always trying to do is optimize our borrower funnel. The faster we can go from an application to cash in the borrower's hand, the better. So let's just say that this is our list of funnel stages. They complete their online application, a bunch of stuff happens, they get their money. These are also the stages as they appear in our Salesforce instance. To go from one stage to another, someone just goes into Salesforce, clicks on a drop-down, and switches to a new stage. So an event stream for stage changes could look something like this. You have an application, and it moves through the funnel. It's going through nicely. It gets to underwriting. The underwriter sees there's something missing and decides to send it back to pre-underwriting to get more data. That's perfectly fine. Pre-underwriter looks at it again, sends it back to underwriting, and it gets funded. Everyone's happy. And then, a few months pass, and someone goes back into Salesforce to update the borrower's email address or something like that. And while they're there, they accidentally click on the drop-down menu and change the stage, and then go, oh, crap, and quickly change it back to funded. So we see this stuff all the time. This is why I call it the thing that happened but didn't actually happen. So this is a real event. This thing did happen in Salesforce, but the stage never really changed. So I just wanted to point out that this is a thing in stream processing. I really wish I had something useful to say here, other than the fact that it happens a lot, and you kind of have to deal with it, and it's a massive pain. So that's basically everything I know. Just want to point out that we're hiring all sorts of data people in all sorts of places. So send me an email there if you have any questions. Rebecca over there, or Nathan at our table can also answer any questions you may have. Any questions? Oh, sorry, I think she's supposed to, she's going to get you the microphone.
So, we tried to use Kafka, right, in one of our use cases because we were getting lots of messages. The problem is that, how to view those messages? Is there any tool available?
The tools are not super robust yet. There's, you basically have various consumer jobs. If you want to kind of look through a stream of data to see what's happening, you often do have to write like a quick and dirty custom job to kind of filter through those messages. Streams has made that a lot easier, but it's still, it's not like a traditional database where you just have a client that you can open up and run a select query.
Yeah, in any of the messaging systems, right? We were using ActiveMQ previously. You can go and see the messages, right? But
right.
Yeah, here there's no way to see that, right?
Oh, there are. You can point. Kafka comes with a bunch of command line tools that let you just like dump the contents of the queue. Like if you can either write a job that actually uses a consumer and filters out what you want, or a lot of the time I just use the command line tool to say, give me everything in this topic, and then I use grep to look through it for the particular IDs I want to see and that kind of thing.
Yes, and probably I didn't understand the use case when we use the PubSub and the streaming, right? The streaming is mainly when we have the joins, right, and those sort of stuff. Is that the case?
It's for a few different things. One, it's also to it gives you a really good way to audit your data. Rather than just having a compacted view of what's happened, like in that example of just having an account balance, by having all the actual transactions that led up to that, it gives you a really good way to, audit, the conclusions that you've come to. If you're ever unsure that the current balance is the balance as it actually should be, you can go back and look at all that data to confirm. I don't know if
how do you go back, by?
So in Kafka, you can keep that data around in the topic for as long as you want. By default, it's there for 7 days.
Yeah.
For a lot of our topics, especially since there's not that much data going through, we just keep it forever. Okay. And so, that data will get backed up to S3 and stuff, but it also just lives in that topic so that we can kind of look at it at any time.
Okay, yeah, thanks a lot.
Hello. Quick question. Do you use any kind of automated testing on those processes, or how you test your code? Do you use any specific tools?
That's a good question. So, from a data point of view, don't use too many specific tools. Mostly just use something to query against the source system, query against the destination system, and kind of make sure everything lines up the way it should. Yes. Oh.
Did you pick Kafka because of the distributed cloud nature of the data, or what? Or because there's a lot of data, therefore you have to find?
It was part of it. I think one of the main reasons was to have that central hub where all our data lived. And so instead of having apps communicate directly to each other and getting that inconsistent data, we just have a central place where everyone writes to and everyone reads from. And so if two different apps want to know something about the same bit of data, they both just consume from the same topic, and they get the exact same view on that data, rather than this app telling this app what it knows and then getting network partitions and that kind of thing. We also did want something that was like fault tolerant and reliable and stuff like that and would scale. I honestly can't speak to which was the primary motivation there.
So is it, I mean, I don't know anything about but is Kafka something that you, I mean, how do you get Kafka if you want to use it?
There's a few different ways. There's services you can use to deploy it for you. Actually, deploying it yourself, you probably need a DevOps team because it's quite involved to run a cluster yourself. There's also AWS has I'm trying to remember the Kinesis, yeah, Kinesis, which is a managed Kafka, and it kind of gives you a subset of Kafka's features with a lot of stuff managed and a lot of extra features which make it really nice to use. Yeah.
Two questions. Do you use open source Kafka, and are you investigating other elements of the SMAC stack?
I think it's the open source. So we do use the Confluent platform, which provides other tools around Kafka. And what was the second part of this?
Do you use any other elements of the SMAC stack, like Spark and Cassandra?
No, we don't. Yeah.
Even in evaluation?
To be honest, that would have been evaluated before I started. So yeah, I'm not too sure, unfortunately. Yeah. Any other questions? Cool. Okay. Thank you very much.
Okay, let's give a big thanks to Dean Morin. Lunch will be starting at 12:30. And it's free. It's provided by one of our sponsors, Data Idol. Oh, we also want to give a big thank you to our sponsors, Funding Circle. So thank you very, very much. And thank you to Dean. And we'll see everybody, I think lunch is 45 minutes, so we'll be starting again at 1:15. Thanks very much.